So let us have the second set of lecture by Cristiane.
Okay, good morning, everybody. It was hard to wake up early. Theoreticians like to sleep, right? Okay, very good. So let's revise a little bit fast what we have seen yesterday. We have seen that if we want to perform a quantum mechanical description of an open system, for which I cannot write a Hamiltonian because energy is not conserved, I cannot apply the usual canonical quantization that we use to build quantum mechanics, right? We can't even use the path integral by Feynman, and we have to resort to some different approach. I wait for a minute until everybody sits down. So the solution that we found, that Caldeira and Leggett found, is to couple the system of interest to a reservoir, because now the system plus reservoir is conserved. So we wrote a Hamiltonian for the entire system. And now what we are going to do today, we are going to find a way to trace the Bath variables and to get the influence of the reservoir on the system of interest to get some effective description. So today we are going to derive what is called the reduced density operator. Okay, so the Hamiltonian that we wrote yesterday consisted of one part for the system with momentum p and coordinates q, plus an interaction term, which was a function of the coordinates of the particle and of the harmonic oscillator, plus the Hamiltonian for the reservoir, which was a function of pk, qk. Okay? So now let's introduce a vector r. Yes, please come fast. So let's introduce a vector r, which is denoting the position of all the n harmonic oscillators, okay? So rk is the position assumed by the coordinate qk. And we are going to use the completeness relation connecting to the system plus reservoir, which is double integral on x prime, r prime, x prime, r prime, r prime. That's right. R prime, r is always a vector, equal to 1. Okay, so the positions for the particle I will denote by x and y, and by the reservoir by r. Okay. I can now write my density operator in coordinate representation I can write as xr rho of t yq. Okay, so my density operator will be propagating my complete system from yq, so y for the particle, q for the reservoir, q is also a vector, up to xr, x for the particle, r for the reservoir. So this is nothing but x prime. Let me write it first because it's very long, and then I explain, okay? Q prime of times okay. So the density operator in coordinate representations, xy for the particle, qr for the bath, is nothing but I replace my rho of q by the expression that I wrote yesterday for you, E2 minus I Hamiltonian T over H bar times rho 0 times E2I Hamiltonian T over H bar. And then I have now inserted in between this completeness relation. So here I inserted y prime q prime integrated in y prime and q prime. And here I inserted x prime r prime and integrated over x prime r prime. Okay? So I just rewrote rho and inserted two completeness relations there. Okay, when I do that, that's very nice because now I can recognize this as the Feynman propagator, K, that is propagating my system with the Hamiltonian H from this state to that. So this is the Feynman propagator, and this I also can recognize as the inverse Feynman propagator, K star, right? So I can then, so those are Feynman propagators. Forward and backward in time. So I can then rewrite this expression for my xr rho of t yq as being simply these four integrals dx prime, dy prime, dr prime, dq prime of the Feynman propagator xrt x prime r prime 0 times the k star of yqt y prime q prime 0 times the x prime r prime rho of 0 yq. No, y prime q prime. Okay. Okay? So this is the Feynman propagator of the entire system from here to here. This is the backward propagator from here to here. So k times k star. And this central part here, which is the initial density operator, rho 0. Okay? So now, what I want, actually I want to eliminate the bath. So I want to take the trace, you remember that I was taking the rho r, I was taking the trace of the reservoir coordinates, right? Because all I am interested in is in the system. So how do I take the trace over all the coordinates? By making q prime and r prime equal to r and summing over all of them. It is just the trace is the sum of the diagonal elements, right? So I have to make them equal and then I integrate. So if I want to take the partial trace over the bath, I am going to now get my row twiddle. So the twiddle means that I have take the trace over R, right? Which is now only a function of X and Y. So XR row of T, YR. Okay? So I have to take here Q equal to R and integrate over all R. That's the meaning of taking the trace. And then I get the reduced density operator, which now depends only on the system coordinates, X and Y. So this is going to be nothing but now 5 integrals in R, which is here. R prime, Q prime. Those are for the reservoir, X prime and Y prime. And then I have these propagators. XRT, X prime, R prime 0, K star of Y, RT, Y prime, Q prime, and 0 times the initial condition, row of 0, Y prime, Q prime. Okay? So it's long, but formally it's quite simple, right? I started from the density operator of system plus reservoir, rewrote this for the ones who have arrived late. I rewrote my row of T as E2 minus I Hamiltonian T, row 0, E2 I Hamiltonian T. I inserted completeness relations here and here. That's why I got these 4 integrals. And now I recognize this as a Feynman propagator from X prime R prime to XR. This is the inverse Feynman propagator. So I get trajectories forwards and backwards. And this is my initial density operator. Good. Then I took the trace over the reservoir. That's why I got row twiddle. Row twiddle is only concerning the system of interest. And for this, I took Q equal to R, and I integrated over R, because that's the diagonal elements. I ended up here. Very good. So now, from here, we'll take the first simplifying hypothesis. And the first simplifying hypothesis is actually a very strong hypothesis. So here you have the density operator of the complete system at time 0. What they are going to assume is what is called a factorizable initial condition. They are going to assume that at t equals 0, this initial density operator can be written as a product of a density operator only for the system times another part only for the bath. Namely, they assume that the bath is in thermal equilibrium, and at time t equals 0 plus, I am connecting the system to the bath. This is a quite rude assumption, because much more natural would be to assume that initially the system and the bath are in thermal equilibrium together, and only then you come and you make a measurement over the system, okay? But this very rough initial condition simplifies your problem enormously, because it will allow you to get an expression that holds always. And then you just change the potential to which your particle is subject to, and you can always use the same expression. So when they first did it, when you are doing a theory before anybody else, you just simplify as much as you can, right? To make your calculations easier. And then you get a student afterwards and you tell your student, okay, now you do the full problem. So that's what they did with me. So my master thesis was to calculate what happens if your initial condition is not factorizable. Then what happens is that you couple Feynman path integrals in real time with the ones in imaginary time. It gets a mess. It gets horrible. And what you gain is very little. So don't go into it. Let's stay here. Okay? Because this gives you really a closed solution to the problem. In the other case, you have to solve it again for every case, for every potential that you have. So here, it's a good, it's a good way to simplify. Okay, very good. So what we are going to assume then is that x prime, r prime, rho of 0, y prime, q prime, which is defined as rho, well, let me just write this directly, as rho system of x prime, y prime, and 0 times rho reservoir, which is r prime, q prime, and 0. Okay? So it's one times the other. So if I now plug this part in here, look how nice. I can rewrite that gigantic thing in a very elegant way. I can now rewrite that my reduced density operator for the particle is simply the integral in x prime, y prime, times some function, j, that I'm going to write to you in a minute, times rho, let me call it rho of x prime. I have rho s, y prime, and 0. And this j is something gigantic. Okay, of x rt x prime r prime 0 times k star of y rt y prime q prime 0 times rho r of r prime q prime and 0. So I separated everything that depended on the bath here, which is the k times the k star times the initial part for the reservoir. And after I will integrate over r, r prime, and q prime, this is going to be just a function of x and y, and x prime, y prime, right? And then I can write the reduced density propagator for the system as a product of the initial density propagator for the system times a super propagator, which is this one that contains all the influence of the bath. Is it clear? One shouldn't get lost into the big expressions. Do you have any question? Okay, very good. Let's try to understand that J is indeed a super propagator. So suppose that the system and the reservoir R and S do not interact. What would happen to J if R and S do not interact? So then I could rewrite my J to be, this K would be a product of the two parts. So I could have a K of a system of x prime, xt x prime 0, times another K of the system star of yt, y prime 0, times all these integrals from the bath in R, R prime, and Q prime, times the propagator for the reservoir, RT, R prime 0, times K star for the reservoir, RT, Q prime 0, times rho R for Q prime, R prime, and 0. Right? So if the system and the reservoir would not be interacting, this K could be written as a K of x prime times a K of R prime. This would be a K of y prime times a K of RQ prime. And the initial density operator for the reservoir. But if this would then be the case, I could immediately recognize this as being the trace over the reservoir of rho R of T. And this is simply 1. So if these two, the system and the reservoir would not be interacting, this would be simply the product of a propagator for the particle times the backward propagator for the particle. That's why it is a super propagator. This is just to visualize that this is a propagator. Okay? If the two things would not be interacting, would be just a product of propagators, but because they are interacting, this is going to be mediated by the interaction with the bath. Are you fine? Very good. Okay. Let me start erasing now. Very good. Okay, so now the things that we actually need to calculate are those. And those are going to be very lengthy expressions, which is simply a Feynman propagator for any plus 1 particles. 1 is my system of interest, and the reservoir has n coordinates. Okay? So everything what we have to do now is to solve path integrals, Gaussian path integrals for any plus 1 particles. That's why we are going to use Feynman, because if you would need to use wave functions in any plus 1 space, it would be quite hard. And using Feynman is very, very easy. Okay? So from now on, the only thing that we are concerned with is to solve this. Because after we solve this, we also solve this, we put here, we have our final expression. We are done. Okay? So let's then so we need to calculate the propagator, the Feynman propagator, k of x r t x prime r prime 0 for the composite system. So this is simply going to be written as a path integral from x prime to x. I am writing my path integrals as a kind of a square S from r prime to r of a trajectory x of t prime, a trajectory r of t prime of the exponential of I over h bar s, which is a functional of x and t and r. Close. Okay, so I'm just formally writing. You propagate from x prime to x, r prime to r, over all possible trajectories, gx of t prime, r of t prime, weighted by the action, where my action, s of x and r, is simply the integral from 0 to t dt prime of my Lagrangian of x dot r dot x. Oops, why do I put here? Don't need this. X and r. Okay, where this is now the part concerning the reservoir plus the system. Very good. Let's start doing it. So I am assuming that x of 0 is x prime and that r of 0 is r prime. So in this thing, I am assuming that x of 0 is x prime, x of t is x, that one, r of 0 is r prime, and r of t is r. Okay, I'm propagating from 0 to t, and these are those functions at 0 and at t. Good. So I can then rewrite, all the time I will be rewriting things because the expressions are so long. So I can then rewrite my j, which is here, this one. Let me get a pink color for you. This is my j. Okay, I can then rewrite my j of x, y, t, x prime, y prime, 0 as the path integral from x prime to x, the path integral from y prime to y, dx of t prime, dy of t prime, e to I s0 x of t prime over h bar, e to minus I s0 of y of t prime over h bar times something that's called an influence functional, y of t prime, which is now going to collect all the parts of the reservoir. Okay, so let me see if you can see what I'm doing. I wait a little bit for you to look. Yeah, if you stop copying, just pay attention. So I can write my k as path integrals, right? Which will now have the total action. I will do the same for my k star that I'm going to put here. When I plug in the action here, I have three terms for the action. I have one part which is S0, that depends only on the system. Then I have an SI, that's the Hamiltonian or the Lagrangian, that depends on the interaction, depends on both. And the H reservoir, that depends on the reservoir. So the parts that are for the interaction and for the reservoir, they are coming inside this influence functional. I can just separate from here the parts which are just for the system itself. Okay? From this K, I take this out, which is S0 for X prime. From the K star, I take out the S0, which is the negative one, because it's K star, it's propagating backward in time, for the Y. And now inside this F, I am going to plug all the rest. Let me write the F for you, because then maybe it gets more clear. Y of t prime, 1, 2, 3, gr, prime, gq prime, and then I have the rho r of r prime, q prime 0, and then I have the path integral from r prime to r. The path integral from q prime to r, because I'm taking the trace. Then I have gr of t prime, gq of t prime, and then I have an exponential of I over h bar times SI, which is a function of x and r, minus SI, which is a function of y and q, plus SR of r, r of t prime, plus, minus SR of q of t prime. And here I close this and I close this. Let's see if I didn't lose you. Okay? So, I had this big truck to calculate, the super propagator, because when I have calculated this super propagator, I will plug it in. I have my initial density operator for the system times the super propagator. I get my density operator, reduce the density operator, with which I can calculate any observable, average value of any observable for the system. But the difficulty is to calculate this. Okay, I have a system of n plus 1 particles. I have the initial density operator for the bath times this k, which is a Feynman propagator for the total system, times the k star, which is the backward propagator. Okay? So I will now write the Feynman propagator, just 1k, which is over there, in terms of path integrals. It is just the integral over the trajectories of the particle times the trajectory of the path averaged by the action for the system and path, where the action is simply the integral in time of the Lagrangian. Right? Good. Now I can then rewrite my superpropagator, which is this one here. So what did I had? I had these three integrals in Q prime, R prime, and R. They are here. They are inside this F. Okay? These are these three integrals. Then I had the rho R at the end here. This is there, here, the rho R for the reservoir. Then I have these propagators, which contain everybody. System, interaction, plus reservoir. So the part for the system I put out. And here I let the part for the interaction and the part for the reservoir. Okay? Then I have the K star, which is the backward. The backward enters with a minus sign. I get the part for the interaction and the part for the system. And the part for the particle itself, I put outside. Is it clear? We are just trying to clean up because it's so long. You have to rewrite in a way that you can handle it every time. Are you bearing with me? Okay, very good. Okay, so now you see, this is my influence functional. That's now where I start solving. Okay? So I separated my rho into a J times rho S. I rewrote my J in this way. The parts for the particle times the influence functional. And now that's the so-called influence functional, which is measuring the influence of the bath on the particle. It's only a function of the particle coordinates containing all the influence of the bath, and that's what we are going to solve now. Very good. So let's solve it. For this, we need to know path integrals. Do you know path integrals? Who does not know how to solve Feynman path integrals? Everybody does. Very good. So you can practice a little bit in the afternoon. So to solve the influence function now, let's first take the kth harmonic oscillator. And then we will consider all of them. Subject to a force Ck x of t. Because of the interaction term being Ck x of t qk of t, I can think that the oscillator is subject, the particle is acting on the oscillator making this force. Okay, so this I can solve, and I hope you will. This is one of the exercises for today. So my propagator concerning the reservoir and the interaction for the kth harmonic oscillator is going to be mk omega k divided by 2 pi ih bar sine of omega k times time to the power 1/2 exponential of I over h bar S classical of k. And now this is going to be one exercise for you for the afternoon, that the S classical for the kth harmonic oscillator is given by mk omega k over 2 sine of omega kt times rk squared plus r prime k squared times cosine omega kt minus 2 rk r prime plus 2 ck rk over mk omega k integral from 0 to t x of t prime sine omega kt prime dt prime plus 2 ck r prime over mk omega k integral from 0 to t x of t prime sine of omega k t minus t prime dt prime minus 2 ck squared over mk squared omega k squared integral from 0 to t dt prime integral from 0 to t prime dt double prime x of t prime x of t double prime sine omega k t prime minus t double prime t minus t prime times sine of omega k t double prime. Okay? Okay. So it's very long. It's all Gaussian, but there are lots of terms. And you can practice your algebra not losing any of them, getting this path integral. It's actually, because it's all Gaussian, it's just like solving the equations of motion and plugging into the action, right? To get that. Okay, so this is part of it. You will get this. You will get then the other one for the y trajectories. And then you get the ones for the reservoir in terms of y and q. After you do all that, you can rewrite. So if you replace everything there, you will be able to rewrite your f. Let me see where I was. My influence functional is here, so I want to let it here. After you replace everything back there, you will be able to rewrite your f of x and y as being the triple integral of the product in k, because this is just for one harmonic oscillator k, okay? But you will have exponential for each of the k, so you can take the product of each one in grk, g prime, gr prime k, gq prime k, times rho r, r prime, q prime, and 0. These are all vectors. Everybody's vector. Times the propagator, the Feynman propagator for the reservoir K of Rk, R prime, K X of T prime times the K star Ri of R prime, no, Rk Q prime K Y. Okay, so after you solve all that, you can rewrite as the product for each of the case harmonic oscillators. Okay. Now, this kind of path integral is governing the mixed motion with x and r's. But you will still have these ones here, because these ones we are assuming, this is the bath itself. And we are assuming that the bath is initially in thermal equilibrium. So if it is initially in thermal equilibrium, this is just an expression that you get by doing a Vick rotation of the time into complex times, and then associating the time to temperature. So if you do this, you can get, let me see, where should I write this? Okay, you could get then, maybe down here, that your rho R, rho for the reservoir of R prime, Q prime, and 0 is the product in K of your rho K's, rho reservoir K for the kth harmonic oscillator of R prime, Q prime, 0, within this case here. And this, I think in the script, there is one mistake here. There is a square root missing. It's product in K of mk omega k divided by 2 pi h bar sine hyperbolic of h bar omega k over kBt. All this to the power 1/2. I think this power 1/2 is missing in the script. Exponential of minus mk omega k over 2 h bar sine hyperbolic mk omega k over kBt times r prime square plus q prime square multiplied by cosh h bar omega k over kBt minus 2 rk prime qk prime. And now here you close. So this you will obtain by doing the path integral for a system in thermal equilibrium. Okay? We will still play a bit more with this tomorrow, I suppose. So this is now just for the bath. It is this times cosh minus this. This is the prefactor in front of everybody. Inside the exponential, it's no longer an exponential with I over h bar, but it's a negative minus 1 over h bar. So it comes from the Euclidean action. And this is the prefactor. And you have one of these for each k. Okay? So, but those are all Gaussian path integrals. And now you can solve all of them. Looks horrible, right? I am sorry, but sometimes theoretical physics has lots of work until you can get to one beautiful final result after days of calculations. But are you following? Are you with me? Is the strategy clear to you? If you have to do this calculation once, you will know how to do. Right? So you separate as much as you can, you put away your system, and you keep the bath, and you keep defining new functions. And the last one that we defined was this influence functional which was here. And now we started rewriting this part, e to is over h bar, this times this path integral over r and q. We start solving them. And we are now rewriting the initial density operator for the system in thermal equilibrium. In this way, those path integrals we have rewritten. Where did we do? There. There, it's up there, right? It's the K that is up there with this classical action. Now we have to plug everything in here to get our final expression. And when you do this, we can already get something which is slightly simpler. Where is it good to erase? Maybe up there, right? Yes. This. Yeah, so what I did, you see here, this was R and this was Q. I made Q equal to R and I integrated over R. So R prime and Q prime are the initial ones. And now I made the final one equal and I integrated. Because here, so now I have to put an expression for this and for this. In the expression for this and for this, I have three terms. Because this is a Feynman propagator. I have S0, Si, and Sr. Exactly. So I separated it over here. I separated S0, and I left inside this F, Si, and Sr. Right? No, this was just a little interval. Please forget about this. This was just one little exercise to say, if the system and the reservoir would not be interacting, I could immediately see that this J was a product of propagators. But this is not true. They interact. So this part here is not just trace of rho equal 1. Okay? This is something I should erase. It was just to help interpreting that J is a superpropagator. Yes, please. No, you don't. No. As I said yesterday, we are assuming that the system with each harmonic oscillator is only interacting weakly. And that's why I represent them as harmonic oscillators. But this does not mean that the particle is only subject to a weak friction or to a weak interaction, because you have an infinite number of harmonic oscillators. And with the weak interaction with each of them, you can still be in the regime of strong interaction. Okay? The weakness only came for the harmonic oscillators, but you have a large number of them. Yes, please. Yes. Yeah. Here, it is just because of that part. What I'm calculating here, so until now, everything I was calculating was concerning this part. Okay? Which is the interaction of the system and the bath. But when I did my factorizable initial condition, I assumed that the reservoir is initially in thermal equilibrium. And the density operator for a reservoir of K harmonic oscillators in thermal equilibrium can be written in this way. It is just like writing the path integral by doing a Vicky rotation. Okay? It's not related to the rest. This is just the way how I can rewrite this term. And I will still do a Vicky rotation with you on the blackboard afterwards. Okay? So then I have to plug everything back. And when I plug everything back, I am going to get something that is shorter. So after solving all Gaussian integrals, you are going to get that your superpropagator can be written x prime to x, I prime to y, gxt prime, dyt prime, exp I over h bar S0 of x of t prime minus S0 of y. And now the part that's coming from the superpropagator is minus integral from 0 to t, from 0 to tau of x of tau minus y of tau times some function, some kernel, alpha I of tau minus sigma, x of sigma plus y of sigma, d tau de sigma, times exponential of minus 1 over h bar. So this one, no, wait a minute, I think I close it too early. This one I don't close here. This is inside, still the exponential of I over h bar. Okay? I have I over h bar S0, S0. This doesn't exist. We do like this. I over h bar, that's multiplying everything. And then exponential of minus 1 over h bar integral 0 to t, 0 to tau, d tau de sigma of x of tau minus y of tau, alpha r of tau minus sigma, x of sigma minus y of sigma. For now, my alpha r, which means the part which is in the real part of the exponential, is summing k ck squared over 2 mk omega k cotangent hyperbolic of h bar omega k over 2 kbt times cosine omega k tau minus sigma all this is argument of the cosine. And my alpha, with the kernel inside the imaginary exponent, is minus summing k, ck squared over 2mk omega k sine of omega k tau minus sigma. Okay? So this is what you are going to get after you replace everything in. And I hope you will do it. I will have guided steps for you in the afternoon. Okay. I think we could, probably we could stop now to let you, yes, please. From 0 to t and from 0 to tau. And the sigma goes from 0 to tau, and then tau goes from 0 to t. Okay? Very good. Do you want to go for a coffee and then I continue afterwards, or yeah? Do you hear me well? Takes a while sometimes. Okay. Very good. So, back, remember where we were? We had written the reduced density operator for the particle as a superpropagator only for the system times the initial density operator for the system. This superpropagator was a gigantic thing that contained exponential of I over h bar of the action only for the particle times an influence functional which contains all the part from the reservoir. Then we have now rewritten, after rewriting the influence functional in terms of path integrals for any reservoir particles, we plugged everything back here. We could then rewrite that part, which is just the action for the particle itself. This part came from the interaction of the reservoir with the particle. I have x minus y. You see, it's quite easy to understand. It's going to depend on differences and sums of the backward and forward trajectories at two different times, tau and sigma. Sigma is being integrated from 0 to tau, and tau is being integrated from 0 to t, times a kernel, which is a function of tau minus sigma. This is inside the exponential of I over h bar. And this part, which is come from the reduced density operator for the reservoir in thermal equilibrium, because it was a Vick rotated path integral, h minus 1 over h bar. Again, it contains for the reservoir x minus y. Is both x minus y? Or did I write anything wrong? No, both are x minus y. Times this alpha r, where now this alpha r and the alpha I contain all the microscopic parts from the bath of harmonic oscillators. Okay? You can also see that oops, here also there, the things which are appearing here, this cotangent hyperbolic of h omega k over kbt, and you get cosines and sines. Okay, so now we have these kernels here written in terms of the ck squared over mk omega k. These are microscopic variables. We don't like them. We would like to replace these in terms of that phenomenological parameter eta that we got out of the spectral function of my bath, right? That I defined yesterday. Okay, so now if you remember the definition of the spectral function J of omega, It was pi ck squared over 2 mk omega k. You can immediately see that we can rewrite alpha r as 1 over pi integral in omega from 0 to the cutoff omega of eta omega cotangent hyperbolic of h bar omega over 2k bt times cosine of omega tau minus sigma, and the same for the alpha I as minus 1 over pi integral from 0 to capital omega g omega of eta omega sine of omega tau minus sigma. And this can be written as eta over pi derivative with respect to tau minus sigma of the integral from 0 to omega of cosine tau minus sigma d omega. Okay? So it allows us to just get rid of this part, and instead of having now a sum over all the discrete frequencies of the harmonic oscillators, we get an integral in omega using the definition of the spectral function. For all purposes, we are going to use that this capital omega is much larger than the typical frequencies of the system, and we are going to put it to infinity. Okay. Now we can replace all these inside that expression for the J. And then there is one part that is a bit specific, where they did some cooking. Very smart cooking. So smart people can do smart cooking. There are certain points in the calculation you don't know very much how to handle, and your intuition gives you the right way to cook. If you do the calculations that I did without assuming any factorizable initial condition, you don't need to do any cooking. But they did the right cooking. So let me do it now with you. So if you look at the imaginary part of the exponent, the one that has that alpha I, after you replace this part, you are going to have, so the imaginary part of exponent, you are going to have eta over pi integral 0 to t integral 0 to tau integral 0 to capital omega x of tau minus y of tau d tau minus sigma of cosine of omega tau minus sigma times x of sigma plus y of sigma let me write this like this, d tau d sigma d omega. Okay? Just replacing this inside that alpha I in that term there. Eta over pi. Okay, but now you can rewrite this as minus eta omega over pi integral from 0 to t of x squared minus y squared d tau plus eta over pi x prime plus y prime. Remember that the x prime and y prime are the x and y at t equals 0. Integral from 0 to t sine of omega tau over tau, x of tau minus y of tau d tau plus eta over pi integral from 0 to t, integral from 0 to tau, x of tau minus y of tau, sine of omega tau minus sigma over tau minus sigma, x dot plus y dot, oops, not of 0, this is sigma, y dot of sigma, d tau, d sigma. Okay? That's the part from the imaginary, that one in the middle here, in that part. This became that. So we have integrated by parts with respect to sigma. Okay. If you look here, this is coming from, the first term comes from this harmonic correction that we had already talked about. Then, this you could use to redefine your potential. It's not a very essential thing. Now, if you think that T is much larger than omega minus 1, so you can push your omega to infinity, you can approximate that 1 over pi sine of omega tau minus sigma over tau minus sigma, you can approximate this by a delta of tau minus sigma. Okay, this is one of the representations of the delta function. But there is one point where we have to pay some attention here. So the second integral, which is that one that we had here, this part, is a bit problematic because it's a not continuous function as a function of the lower bound of integration. Okay? So let's rewrite it, that one, the pink. If I use the delta function, I'm going to get eta over pi x prime plus y prime. Then I have the integral from 0 to t of a delta of tau times x of tau minus y of tau d tau. Right? But when I have this, now look at this. If I rewrite this integral, instead of having 0 here, I put a t prime. If my t prime is bigger than 0, if I would start from t0 plus, this would give me 0, because the delta function for t prime bigger than 0 would always kill everything, right? So this would give me 0 if t prime is bigger than 0. But if t prime is precisely equal than 0, this is going to give me eta times x prime squared minus y prime squared divided by 2. Because then this would now kill it except at the point at which my x is equal to 0, and I get the product of this with this. Okay, oops, there is a pi too much here. Sorry, this pi has disappeared because this went into the 1 over pi into the delta. Okay, there is no pi there. And the factor 1/2 is because my delta function is being integrated not from minus to plus infinity. Every time you'll be missing factors 1/2 in the calculations, remember the delta function. Okay, so now here, if I am including the 0 or not, I am going to get a very different answer. Okay? And they knew that you shouldn't include. So their assumption is that you are connecting your system to your reservoir. So system plus reservoir connected at a time t equal 0 plus, in a way that they can take this integral to 0. As I said, it is a cooking. If you take the full initial condition, you don't need to cook anything. Everything comes out straightforwardly, but it's a well-cooked thing. The intuition was very good. Okay. Now, for the third integral, so the second one goes away. The first one is just renormalizing the potential. The second one goes away. The third one, it's going to remain. If in the third one I keep the 0, nothing changes because it's tau minus sigma, everything is fine, we have no trouble. And then to get the right boundary conditions, you can say that your superpropagator fxy 0 plus x prime y prime 0 is a delta of x minus x prime. This is the initial condition. Okay? So for this, we have to perform the integrals in the regime where those are bigger than 0 and the smaller or equal than t. Very good. And then this one, you are going to take the solution, which is the 0. Very good. When you do this, your final answer for your superpropagator is going to be, we got there now. Just get a coffee. We then get our final answer that our superpropagator is exponential of minus I over h bar times some function of xy, x prime, y prime. These are the initial and the final positions of the particle times the path integral for the particle from x prime to x, from y prime to y, dx to prime, dy to prime, e to I over h bar S0 of x minus S0 of y of t prime. And then we have exponential of I over h bar times minus m gamma integral from 0 to t of xy dot minus yx dot dt prime times exponential of minus 1 over h bar times 2m gamma over pi integral from 0 to capital omega d omega, omega cotangent hyperbolic of h omega over kbt times integral from 0 to t d tau integral from 0 to tau d sigma times x of tau minus y of tau cosine of omega tau minus sigma times x of sigma minus y of sigma. And that's it, where I have defined that gamma is eta over 2 times the mass. This is this relaxation constant, and that f, that function f, so the function f can be written as m gamma over 2 x squared minus x prime squared minus y squared minus y prime squared. Okay? Okay, that's our main result. So this is just some exponential prefactor that depends on the particle. Then we still have here these path integrals to solve, which now depend on the initial action for the particle, okay? We just got rid of the part of the harmonic oscillators. That was the bath. Here, I will need to solve depending on which kind of potential my particle is subject to. Is it a free particle, a harmonic potential particle, harmonic potential for the particle, or something else? This is still inside S naught, the external potential to which the particle is subject to. The only part we solved is the harmonic potentials of the bath. Yes, 2 questions. Yes, at the end here, right? E to minus IF times the path integral. Yes, thank you. It is there. Yeah. And then I have the path integral for the other part. And then I have this exponential. And then I have the other exponential, which is also missing a bracket. All this is inside the exponential. Yes, but wait, first there was one there. The brackets, thank you. Diego. X tau minus y tau, x sigma minus y sigma. That was minus and minus for the part. The other one is minus and plus, but this part was minus and minus. Okay. Okay, very good. So now, yes, please. Yeah. Yes, these are trajectories of the particle. Mm-hmm.
At some point you define the J of omega that can be also equal to the imaginary part of the Fourier.
Yes, yes. Yes. Yeah, so that commutator is the force that the particle is acting on the bath. That was the ck times x of t, right? So that's the force that each harmonic oscillator feels because of the coupling to the particle. It comes from the interaction term. It is a correlation function, yes. Yeah, so you get it's a 2-point correlation function, and then you take the average value of it, the Fourier transform, and the imaginary part of it. No. It's the statistical, yeah. Yes. Yeah, any other question? Okay, very good. Yes, please. Uh-huh. 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 Yeah, so for instance, we are taking the bath, which is as simple as possible, right? If I would decouple them, I would get just the propagator of the particle itself, because our bath would trace to one. That's what I did before, right? Now, how easier bath can we take? Ah, you can take. Yes, yes. So, yeah. So now let's just start thinking, what kind of bath could I take? Could I take a more general bath? It was also a question that Diego had, right? So I can try to generalize my problem in many different ways. One way that I can generalize is via the spectral function, because the spectral function is in a way telling me the ways how I can excite the bath, right? It's telling me which are the frequencies, what kind of frequencies can I excite in my bath. That is at the end, at the boiling end, the thing that's carrying the properties of my bath, okay? So we are taking something extremely simple, which is eta omega, right? It's just linear in frequency. You could think of taking something more complicated. It's still power law. You could take omega square. If you take omega square, this 2, which is in the power of the omega, is the order of the derivative that comes in the Langevin equation. So instead of getting a friction, which is dx dt of the position, okay, x dot, I will get x double dot. I would renormalize the mass. But suppose I take x omega to the power 3. I would get, instead of the Langevin equation, a friction term, which is x triple dot. Have you ever seen this? Abraham-Lorentz equation of an electron interacting with its own radiation field. This would correspond to a bath with a frequency omega cubic. Okay? You could think, I could take a more generic bath, like something exponential, such that all these power laws would be an expansion of my bath. Or I could even take a more generic bath, which could be a log. So we have shown a few years ago that you can take, log baths are super interesting. You can take baths that could reproduce in a certain limit a Brownian motion, and in another limit, a Levy flight. What is a Levy flight? So you have that the Brownian motion is doing this. But it's possible that sometimes you do a long flight, and then you have Brownian again. Another long flight, Brownian again. Another long flight, Brownian again. It is Brownian on 2 different length scales. Because if you zoom out, each of these long flights also looks like Brownian, right? So you get Brownian. This is the so-called Levy flight. It's Brownian on a small scale and Brownian on a large scale. So if you take a more complicated type of spectral function, you could describe Levy in one limit and Brownian in another limit. Okay? And what I am going to tell you tomorrow, we are now going to take more complicated spectral functions, eta omega to the power s, where s is no integer. Because for s equal 1, it's Langevin, proportional to the velocity. S equal 2, you renormalize the mass. It's just a term like x double dot. That's multiplied by the mass, right? S equal 3 is Abraham Lorentz. So what happens for S arbitrary? Between 1 and 2, for instance. That's one of the things that we did a few years ago. Okay, so I will try to give you like square root or something like this. S to 1/2. That is another way to generalize the bath. So basically, one way to think of this bath is you touch the J of omega. You could instead keep your bath as harmonic and touch the interaction term, right? You say, I couple the two not via coordinate, or coordinate velocity, but via coordinate S derivative of the harmonic position, which could be also a fraction. This was the master thesis of a student that I supervised last year. Okay? So you can generalize it in many ways. There is also a very beautiful work by the guys in Trieste, I think, where you couple your system to a bath and you couple the bath to another bath, like a fractal structure in the bath, in the reservoir, by coupling one harmonic to more. So you can think of many ways how you could play with that. But maybe the easiest is just to play with the eta omega. Yes? Any more question? Okay. So, yes, please. To do how? Yes, that is also an interest. That's not a very easy one, right? So you have here a particle with a set of independent harmonic oscillators, right? Now, he wants to put another spring here. I don't know if anyone ever did. Good luck. Yeah, but it's also interesting. So they are no longer independent, but they are interacting. You could get them interacting 2 by 2 or more, right? Okay. Yes, please. Ah, yeah, so I would get that other term there. Just that term. You would get that term more, which is now depending on x prime minus y prime squared. Wait. So this is just the assumption for starting at t equals 0 plus, coupling the system to the reservoir at t equals 0 plus, right? So if I would let the system get in contact with the reservoir and let them reach thermal equilibrium together, and only then I come and I measure the position of my particle, for instance. Then what I will get, and you could look at my paper with Caldera, it's a very, very old paper. I was very young when I did it, 21. So you will see that all these path integrals in real time will get coupled with the path integrals at imaginary time. Because until now, we have been writing just the reduced density operator in equilibrium in terms of that path integral. So this part was just for rho r, right? Now you have to keep both. So you will couple all these trajectories, backward, forward, real and imaginary. It's horrible, but it's possible. And then you don't need any simplifying assumption there for 0 plus. Exactly. That is the way. Yep. Yes. More questions? Very good. Maybe you think more. Let me see if I finished everything here. Yeah, I think I did. Actually, I finished everything. Now, I will tomorrow. I think this part I will not do. Yeah, so tomorrow I will then just start with the Vicky rotation, reminding you, and then calculating the reduced density operator in equilibrium. I wanted to get this expression for you, to get a final expression for this density operator. So here we got the J, right? We'll get back into the row and get a closed expression for it. That's one thing I want to do tomorrow. And then instead of going through the applications that I have in the script, have you seen the script? Did you get it? Okay, so I think probably instead of going through these applications I had in the script, I will have then a 1 hour with the slides showing you the fractional case. Okay, because maybe it's more interesting. And this one you can still take a look there. I will be here until the end of the week if you want to discuss any of these cases of macroscopic quantum tunneling or so on. I could. If any of you needs more information about the Josephson junction and the derivations for the squid, I have my handwritten lecture notes, which contains more detail than the typed lecture notes. I could scan for you. Okay, just let me know. I could just send me an email because you have my email now. Okay, very good. I think that was what I wanted to tell you today. Any other question? I apologize for all the long. Yes, please. So it was not like this. We had a more complicated. So you can look for Mulder, Caracanhas, and myself on archive. You find it. It's a more complicated function with a log and so on. It was really complex. But then it was connected to some function that Peter Zoller had while describing experiments on cold atoms. So it connects to reality. Levy flights are usually measured experimentally in cold atoms. Okay, but there you can find the reference. Yes, please. Yes, we are going to get an expression for it tomorrow, and you will see how elegant it turns out. At the end, we are going to get one term, which is the so-called Caldera-Leggett action, which is going to be something which is non-local, which is describing friction. So I told you there is no way I can write a Lagrangian for my system because my system is open, right? Actually, there is. After I couple it to the reservoir and I integrate out the reservoir, I can get a Caldera-Leggett term that's going to describe dissipation. I will get it tomorrow. And you will see that it is non-local, and the fact it's non-local, it's because I integrated out parts of the degrees of freedom of the system. It's a kernel. Tomorrow I get there. It will be a very elegant and simple one final term. But I still need to work out a bit more for you. Yes? Any more question? Yes, please. Yes. Um, the initial condition in which way? Ah.
on the opposite side, so very entangled.
Yes, it would. Yes, it would. It would, because we took this, you see, all this term here is coming from the assumption that the reservoir was in equilibrium, right? There is also one case, I forgot to tell you, which is very interesting. Suppose that instead of taking a reservoir of harmonic oscillators, I truncate it and I take only a two-level system as a reservoir. So it turns out that now my spectral function is going to depend on temperature. This J of omega will have a term with a tangent hyperbolic of h omega over kBt. And now, so I have lots of harmonic oscillators with frequencies omega k, right? Now it will be such that by tuning the temperature, I control which frequencies are coupling more strongly or less strongly. So I get a way to tune the coupling to the bath, which is super interesting, which is not in here. Okay, you can get some temperature dependence in the spectral function to select the frequencies which are more important depending on whether the temperature is higher or lower. That is also one thing that one could do. And another thing that they were trying, you see, the first guys who were trying to build qubits using Josephson junctions, and that's also when all this started because of the issues of decoherence and dephasing. One of the techniques that they tried was to couple, first of all, an unharmonic oscillator. You have a system coupled to an unharmonic oscillator and then to the reservoir. Because this, by bringing nonlinearities, this allows you to tune further your system. You can filter some parts of the spectral function. Yes? Okay, if you have more questions, we can talk in the afternoon because I think my time is over. Let's give the place to Gregory. Thank you.